All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hope you guys are doing okay. Was waiting until a few more people sign in. We have a handful of people still missing, but I think I'll just move on and then maybe we can do the activity towards the end. Yeah, so, all right. What I would do instead is let's just start jumping into it. Make sure that I can see the chat here. Okay, I think everything's set up. All right, so let's jump into it. Hopefully you guys had a good week or a good couple weeks. Sorry about a mix-up last week. There was like construction literally right outside my window, and it was like I couldn't even hear myself. So it just wouldn't have worked. And I would have just gone over the test anyway, which is what we're going to do today. But before that, I just want to make sure to get a few announcements out of the way. So remember to fill out that doodle poll for the session on Friday. And remind me to put you in groups later. I was going to do it in the beginning, but since there's still people missing, I think I'll move that towards the end. So after I finish going through the quiz, I'll give you guys a second to actually meet up with your groups. So you should have seen an email from me late last night about study groups. I'll talk about what those are and have you guys connect with your groups later. But we'll do it later. Hopefully whoever's missing will show up. Test 2 is on Wednesday, just to give you a time of scale and a schedule. December 2nd during regular class time. The final is on Wednesday, December 16th at 9:30. Okay, so that is still according to, it's from the official schedule on the Fordham website, but according to them, it's still tentative, even though I don't expect it to change. Keep checking for changes to that date. As well as a week ago, maybe a little more than that, you may have seen an email from Piazza from me. That's just another forum. Been trying to find creative ways to get people to engage and just start collaborating. And so that's what that is. It's pretty much like a forum platform where you guys can all go and talk. So you can ask your questions there, and you can get feedback from me as well as other students in the class who are doing well. And yeah, thought that would be a good thing to try for some of you, especially since we're going into the last few weeks of finals, and you might have questions where you can't get in touch with me at the moment to answer. That might be a good option. So yeah, I just want to make those announcements, make sure we're all aware of that. And yeah, remind me to do the whole group thing later. You guys should have seen the email, so you should know already what group you're in. And so later on, what I'm going to do is I'm going to break you guys out into breakout rooms. You guys will all go to the rooms, and the point will be to exchange contact information. It'll only be a few minutes. So just make sure that you guys all know how to contact each other. And then during that time, which is, I don't know, 3 minutes, 5 minutes, something like that, you guys can decide when you're going to meet up, or just decide that, hey, we'll all reach out and decide when to meet up later or something like that. Yeah, so I really want you guys to have like a hub or a group or a tribe moving into finals week. You have a bunch of people who are going through the same thing you're going through, willing to offer advice, willing to help each other out. You guys are all in the same class. You're all in the same boat. You're all striving for the same thing. So yeah, help each other out. Both those people giving help as well as getting help will benefit. I can tell you that from experience. Anyone who has been a teacher or a tutor can tell you for sure. A lot of times you learn the most when you're teaching other people, right? So when people ask you questions and you have to reach into your mind and formulate an answer that's not just an answer that you would be able to understand, but this other person who is not in your mind would be able to also understand. It forces you to have to organize knowledge in your own head in a certain way that is very beneficial. And then you're going to start realizing that people ask you questions about things that you've never thought about. And then now you have to think about the knowledge that you thought you knew in a different way. And you're like, oh, that's interesting. That's an interesting question. Yeah, I think this would have to be true because I know this is, and it gives you more command of the material because you now have to explain something coherently to someone who's not you. And yeah, I think it'll be very helpful. So whether you're giving help or getting help, when it comes to the pursuit of knowledge, it's going to benefit you. So I think a forum is kind of a nice way to do that, where students can ask for help and other students can pitch in. And at the end of the day, I'd be able to see the answers that people are giving you, and I'd be able to endorse the answer or to add to the answer or something like that. Yeah, so that's what that is. And the groups is another prong on that idea. Okay, that being said, like I said, the main agenda for today is to just get through the fifth quiz, which in terms of the number of questions was not the longest quiz around, but the questions were more hefty this time around, right? There were word problems. You kind of had to set things out a little bit more carefully. It wasn't just a lot of straightforward calculations. So that was the challenge. But we will see how you guys do, and we'll talk a little bit later about the group things. So yeah, it's been a long time since I've actually looked at this. I don't even remember what I asked you guys in the quiz. So let's, this should be fun. Let's go through it. All right, so the first was a select all that applies. I asked you to read some. Okay, I for some reason I feel like I forgot to hit the record button, but I just checked and it's still there. Okay, so I gave you guys some statements. I asked you to select which ones were true, and yeah, just that's all. So a graph can never cross its horizontal asymptote. This is not true. Graphs can cross their horizontal asymptotes. They do it all the time, and I believe in the handout that I gave you. There was an example where if you sketch the graph, you'd realize it did cross its horizontal asymptotes. So graphs can do that. Graphs can never cross their vertical asymptotes. Now it turns out that this is not true, but I will admit that that is kind of tricky. It's tricky in the sense that all the graphs that I asked you about in class that we actually did a sketch for, or I asked you to do a sketch for, they never cross the vertical asymptotes. And it's because you found the vertical asymptotes by setting the denominator equal to 0. So, you know, the denominator can't be equal to 0. So you might have the inkling that you can't cross the vertical asymptotes because it's where your denominator is equal to 0. However, if you look at the definition of what a vertical asymptote is, denominator equals 0 is not the definition. It just happens to be something that for rational functions is a shortcut to finding where the vertical asymptotes are. So that one is a bit tricky. And I'm willing to, if you get everything else right and you actually clicked on this one, I'm probably willing to give you half credit for that if you reach out. But yeah, I do get that's tricky, but I want you to understand that that's not true. So you can have a piecewise function where you just artificially put something on the vertical asymptote. So you can graph 1 over x minus 1, which of course has a vertical asymptote at x equals 1, but then you can just make that into a piecewise function and say, oh, I force the function to be the value of 0 when x equals 1. And you can literally just fill in a dot that's on that asymptote, and you've now crossed the vertical asymptote. It's actually not crazy or anything like mystical that you have to do here. It's really easy to actually cross a vertical asymptote if you want to. It's just that for the kinds of functions, if it's a rational function, then rational functions specifically never cross their vertical asymptotes. functions in general can. Is it possible for a continuous function on an interval to not have an absolute extrema on that interval? This is not true. And there's a theorem called the extreme value theorem that tells us quite the opposite. Extreme value theorem. We'll give half credit if this is the only thing you got wrong. Okay, right. Which normally on the quizzes don't really give partial credit, but I will in this case because it is. To be fair, I did mention this in class, but it's one of those things where if I just say something verbally and I don't actually write it down or give any examples, it's kind of, even when I write things down, students don't pay attention to me. So they're definitely not going to pay attention to something I just verbally said in a few seconds and then moved on. So I'll be lenient here. If f of x is a function such that the derivative is positive when x is less than a, right? So we're at a situation where at a, the derivative is positive over here and negative over here, then f has a maximum at a. This is also not true. F has to be continuous at the point. You could have a situation where the function is going like this, like an asymptote. You could have a vertical asymptote there that you don't touch. You could also have like a hole, right? So you need continuity at the point. You need the function itself to exist at the point in order for that to be true. This was a part of the first derivative test. If a function has a maximum point at x equals a, then the derivative at a must be 0. This is not true. Examples are things with sharp corners. So you can have a maximum point there where the derivative does not exist. So an example, if you want a concrete example, like y equals the negative of absolute value of x, right? So that graph would look like that, where it's a max at the origin, but y prime does not exist. Right, so we saw that at maximums and minimums, you might not exist. We looked at when the derivative does and does not exist, and at sharp corners is one of them. So if your maximum point happens to be a sharp corner, your derivative is not going to be 0. This is something where students often run into this problem because of Fermat's theorem, which goes the other way. Fermat's theorem says if the derivative exists and it's equal to 0, then if you have a maximum and the derivative exists, then the derivative must be 0. And you have to be careful of mathematical statements like that because they are very, and this is one of the things which, I don't know, maybe I might touch on Friday, which does trip people up because English and just language in general, when it comes to mathematics, is very specific. The word order and just basically, a mathematical theorem will say exactly what it means. And in everyday human language, this is not the case. Meanings are kind of fluid. You have sarcasm, you have all sorts of things. People can say things and they mean something different. So things will have colloquial meanings even when they don't have a direct meaning. And so a lot of times people loosely read mathematical statements and they just feel like, well, as long as they mention all these buzzwords, they're saying the same thing. It's not true in mathematics. It's very important how the sentence is constructed, right? Which is one of those things that I mentioned on those Friday sessions, how you really have to be, it's not just being too pedantic or someone wanting to over stress you with details. The details actually do matter, like how a sentence is constructed, what is the word order, what comes after the comma, right? If blank, then blank is different from if the other blank, then the first blank, right? So things like that, you have to be very, very careful. You might know Fermat's theorem, and that might trip you up, but you have to be careful what was stated in Fermat's theorem. Yeah. Okay, so if f is a continuous function with f prime of 3 equals 0, then f has a maximum or minimum point at it. That's also not true. Want a concrete example? Well, the example that immediately comes to mind where a derivative would be 0, where it's not a max or min, is x cubed at the origin. So I can probably even just shift the x cubed. So think of y equals x minus 3 cubed. So that's a guy where at 3, he's going to look like that, right? And if you were to check the derivative at 3, you would get 0, but it's not a max or min. So this is why the first derivative test was important, because just finding the critical points where the derivative was 0 or undefined wasn't enough. You did have to make sure to check if something was a maximum, you had to make sure that the derivative was 0 or undefined at the point. You're increasing on the left, decreasing on the right, and the function is continuous at the point. With all those checks, then you can conclude something is a maximum or minimum. You cannot do that before. If a function is continuous at x equals a, then it is differentiable at x equals a. We also know that's not true. Think of y equals the absolute value x at x equals 0. Quintessential example for where you can be continuous but not differentiable. So it turns out the actual answer to all these sentences was none of the above. Now, it's also true that all of these sentences kind of feel like they would be true, but they're only true to someone who's not paying as much attention as they should be. Okay, so very sneaky. So like I said, it's not just sneaky, it's really to illustrate a point that certain things that I stress, there are reasons that I stress them. And anyone would stress that. So when you want to memorize a formula or a theorem or a sentence or a mathematical definition, you need to really actually be careful to memorize it exactly. It's not like it's memorizing stuff for math is different from memorizing something from history or something like that. Like you can tell us the same story in many different ways and stay true to the essence of the story. With math, that's not true. Like if you don't say things exactly, it's not true. Math actually has logic built into the example, which is why one of the reasons why it can be very challenging, because everyone approaches math as if we're talking like everyday language, me talking to a friend or me talking to everyone else. No, the rules of language and math, very important. Okay, I've rambled on enough. Let's actually get through the rest of this here. Okay, the length of a rectangle is increasing at 7 feet per second. The width is decreasing at a rate of 3 feet per second. At one time, the length is 12 feet and the diagonal is 13 feet. At this time, how fast is the perimeter changing? Okay, so this is a related rates problem. By reading that, you should recognize that. So one, we have a process for this, read. So we know that this is related rates. Two, maybe try to draw a diagram just to see things here. So they told us about some rectangle. Let me call these things something. So the width and the length are changing. They also mentioned the diameter. So let me put in a diameter here. I'm not sure where that's going to come up, but that's the picture. 3, you write down what you know, what you want to find. So according to this, the length, let's say x is the length. That's the horizontal part. Let's call the length x and the width y and the diagonal z. You don't have to call them these letters, but you need to call them something. Okay. Now, what do we know? The length is increasing at a rate of 7, which means I know dx dt is 7. The width is decreasing at 3, which means dy dt is -3. Pay attention to the minus. At one time, the length is 12 feet. So we want the perimeter. So we also know here the perimeter is just going to be 2x plus 2y. We want dp dt when x is 12 and the diagonal is 13. At this time, how fast is the perimeter changing? Okay, so that's that. Fourth, we know that we should come up with the equation. The equation of the thing we care about is the perimeter. Fifth, we know we should differentiate with respect to t. So this means dp dt equals 2 dx dt plus 2 dy dt. And 6, now we plug in. And you'll notice here, something very strange happened. I didn't actually need the values that were given, the x and the z values, because dp dt only depends on dx dt and dy dt. So this was actually a little bit easier than the problems that I usually give you guys. I'm literally going to plug in the 7 here and the -3 there. And that's going to be the answer. So that would be, is that 8? Right, because I can factor out a common 2. What's left over is 7 minus 3, which is 4. So it's 2 times 4, which is 8. And I mentioned that I don't care about the units, but I put them there just for completeness. So that's that one. And as always, you can stop me if something isn't clear. 3. So 3 had a lot of parts to it, but it's really still one problem, but I just wanted to see, do you know about every part of going through the problem? It's going to be hard to move things on the tablet. Let me move it on the other screen. There we go. Okay. So a 10-foot ladder rests against a vertical wall. The Joker, trying to escape Batman, scurries up the ladder at 2 feet per second. As he gets to the top, Batman pulls the foot of the ladder along the ground away from the wall at 3 feet per second. So he's trying to pull the ladder so the Joker falls down. Okay, we want to know when the foot of the ladder is 6 feet from the wall, how fast is the Joker at the top of the ladder falling? Okay, so let x, so here I'm telling you what variables I want you to use. X measures the distance the foot of the ladder is away from the wall. Y measure the height that the top of the ladder is on the wall. Answer the following. Formulate the problem mathematically. Which right triangle diagram best describes the scenario above? So I gave you a lot of options here. If you were setting this problem up, what is the best diagram to draw? So all of these are right triangle diagrams, which is the right shape to draw. But I also spoke in the handout about correctly labeling your diagram and hence avoiding common mistakes that students will get into by not correctly labeling their diagram. And the ladder is 10 feet. X is the distance from the foot of the ladder from the wall. Y is the distance up the wall. So this is the correct. This is the correct diagram here. Okay. So again, when it comes to mathematics, the devil is in the details. So even though you kind of have the same picture, labeling it, being very specific with how you're using notation is going to be very important. Students who label things with the derivatives or with words or with numbers in place of things that are changing where they should be variables tend to make mistakes. You tend to kind of reason through the problem using the notation that you use to set up the problem. And I've seen all of these lead to errors in the past. dx dt, how fast is that moving? So dx dt is this guy. Well, dx dt is the rate at which that guy is changing. That's the distance the foot of the ladder is away from the wall. We know that Batman is pulling the ladder away from the wall at 3 feet per second. Now, if you look at the ladder, Batman is pulling this way. So you know x gets larger as Batman pulls. So you're increasing, therefore your dx dt is a positive 3. If the problem said Batman pushed the foot of the ladder towards the wall, negative 3 would have been the correct answer. Before differentiating, which equation describes the situation? So here I'm asking about the equation that you would put in step 4. So your equation is going to be based on this diagram, which Pythagoras' theorem, right? X squared plus y squared equals 100 squared. 10 squared. 10 squared is 100. So that's easy. Right, so it's one problem you're just going through. I just want to make sure, do you know how to identify each phase in the problem? How fast is the Joker falling down? So here you have to finish the problem. So here you would just continue by moving on to step 5, differentiating. So in here we would have 2x plus 2y equals 0. Sorry, I'm messing up now. 2x dx dt, because we're differentiating with respect to t, plus 2y dy dt equals 0, because derivative of 10 squared is 0, which is the danger of students labeling the part with the ladder with z or another variable, because over here they'd have 2z dz dt, then they'd get confused about what to do with that. And it's like, well, your dz dt is 0 technically because the ladder isn't growing. And so you get that side equals 0. But students who usually write a different variable in this position usually never reasons that far along, and they just get confused and they're like, can't answer this problem. I don't have enough information, when you actually do. And it all stems from a mislabeling of the problem. So that's a very common mistake I see all the time. So now x, we know that x is 6. Okay, so we want, and this is really from step 3, we want dy dt when x equals 6. So notice that we need to know y, not y as in why, but we need to know y. So as mentioned, we always go back to step 4, which is the equation to figure that out. So x squared plus y squared equals 10 squared. So if your x is 6, this means that your y is going to be 8. It's not the answer. It's a 3, 4, 5 triangle. And so, right, so if one side is 3, one leg is 3, the other leg is 4, then the hypotenuse must be 5. Notice that 6 is 2 times 3, which means the other leg needs to be 2 times 4 in order to get 2 times 5, which is 10, which we know is the length of the ladder. So it's a 3, 4, 5 triangle. So we know that y equals 8. So now we move to step 6. So it's kind of like me doing the numbers out of order here, but that's because I actually forced you to go in the certain order with the previous problems. So now you're sort of stitching all these little things together to come up with the answer. So now you move to the plug-in phase. So we're going to plug in 6 for x. Dx dt we knew was 3. Eight for y, dy dt we don't know. In fact, that's what we want to find. You can divide both sides by 2, right? So it'll cancel all those guys. And so your dy dt is going to end up being minus 6 times 3, move to that side, then divided by 8. And 2 into 8 goes 4 times, 2 into 6 goes 3 times. So you get minus 9 over 4. And that's what we put here. So that was problem 3, how you'd get through it. Hopefully that wasn't so bad. Moving on to question 4. This one also had several parts. Maybe I'll move it on the other screen again. It's easier to move when I have access to the keyboard. I can hold down the control button. Okay, Jhevon needs to build a pen in his backyard to hold a llama. He bought a traveling circle actually. Okay, he has 20 feet of fencing and he wants to build a rectangular enclosure where the side of his house forms one of the sides. He needs no fencing on that side. X is the length of the side parallel to his house. Y is the length of the side perpendicular to his house. Use calculus to figure out the maximum possible area enclosed. Of course, step 1 is to read. You'd realize that this is an optimization problem. 2, diagram would be useful. So here's the house, and there's a rectangular fence being built along it, and we're told that this length here is X, while these lengths here are Y. Yeah, okay. So now 3, third step here is to come up with constraint equations and objective equations. And that's what 4.1 and 4.2 is asking you about, right? So 4.1 and 4.2 is seeing, can you set up step 3? What is the constraint equation in the situation? What is the objective equation in the situation? So in this situation, remember, the constraint is the restriction. It's the thing that's given that you can't control, which in this case is the amount of fencing I have. I have 20 feet of fencing. I can't use as much fencing as I want. I'm limited to 20 feet. It's what's given. It's my constraint. It's my restriction. I can only use up 20 feet. Of course, I'm going to use up all of it because I want the maximum possible area. So the constraint is actually the perimeter. So the constraint in this case is the perimeter, which in this case is going to be X plus 2Y. And I need X plus So it's x plus 2y equals 20. And that's option here. Now I come up with the objective equation. So for the objective, it's what we want to maximize or minimize. And if we read the problem, it says, figure out the maximum possible area. So the objective is to maximize area. But the area equation is going to be the one you want. And of course, it's a rectangle, so it's length times width. So it's a equals x times y. In square feet, what is the maximum possible area? So now we have to actually figure out the other steps. So remember what we do is so we're going to create a new objective that's in one variable. So we're going to solve for one variable in the constraint. So let's solve for x. And plug that into the objective. And so that's my new A. So now I'm going to want to maximize the objective. Now, we know this is a parabola. Yes, you could have used that to double check your answer. It's an upside down parabola, so the vertex is what you're going to want. Max that vertex. So I actually know what the answer is going to be, but we're asked to use calculus, so I'm going to actually show you the calculus way. So we're going to use calculus. So calculus, when we want to maximize, we're going to find critical points and set a prime equals 0 or undefined. It's never undefined because it's a prime is going to be a polynomial. So if now I set it equal to 0, so you would end up with y equals 5. And you can check this as a max. But strictly speaking, not necessary in a class like this. If you only get one answer, that's going to be the answer. So now 6, you go and you answer the question. So the question asked us for dimensions. No, in square feet, what is the maximum area? So I actually care about the A value. So I'm actually not going to waste my time finding the X. I don't need to find the X because I do know that my A is 20y minus y squared, 2y squared. So now I'm just going to plug in. So now I'm just going to plug in the 5 I just found. Okay, so I guess I could factor out a common 5 here. And that's 50. So 50 is the answer. Ugh. Okay, So problem 5 is also a big one, but it's again, it's working through the same problem, but I just want to make sure that you guys are aware of all the steps. Because like on a test, I'm going to actually have you write out all the steps. So I really need to make sure you guys knew all the steps. Let me move it on this other screen here. I think I made a mistake. Okay. I think we're fine now. And if at the time you were doing this, you were just like really annoyed by how long problem 5 is, in a weird way, that means I succeeded. Because in-person classes, when you're actually writing everything out, this kind of problem is actually the longest kind of problem that you would do in this course, like in general. Like these curve sketching problems, they are the longest problems. So usually when you're like on a final and you're getting through a bunch of problems in 2 minutes and 5 minutes and 10 minutes and stuff like that, a curve sketching problem would literally take you like 15 to 20 minutes to do one problem. So so I have successfully recreated the experience. If you actually felt like, oh my God, this problem is not ending, I've actually, in a weird way, I've actually succeeded. It's supposed to feel long, like literally curve sketching in an applied calc class or in a calc 1 class in general. It is the longest kind of problem that you're going to have to go through. So yeah, if you felt that way on the quiz, it was actually a good thing. You're getting the usual experience. So let's actually keep going. So I gave you a function. I gave you the first and second derivative. You don't have to verify them. And I'm just going to ask you a bunch of questions about it, things that you should be able to know. So what are the vertical asymptotes? So this is a rational function. We know the vertical asymptotes occur where the denominator equals 0. Hopefully the numerator is not 0 at the same time. Here you can see in the original function that here you just want x squared minus 4 equals 0, which is the denominator of the original, which means your x is going to be minus 2 comma plus 2. So the instructions were, if there were several, arrange from lowest to highest, separate by commas. So you would type minus 2 comma 2 there. Horizontal asymptotes. So we knew that the horizontal asymptote, what you should be thinking of is the limit as x approaches infinity of your function, and the limit as x approaches minus infinity of your function. Your function is a rational function. It's a ratio of polynomials. So we know a shortcut for that. If the highest power is on the bottom, it goes to 0. So y equals 0 is the answer here. What are the intervals of increase and decrease? Okay, so here we have to do a little bit of calculations. Let me create some space here. So for 5.3 and 5.4, what you're going to do is the first derivative test. That tells you about increasing and decreasing. So for 5.3 and 5.4, what you would do is the first derivative test. And luckily for us, we're given the derivative. I'm not taking any chances of copying that down wrong. Okay, so we're given the derivative. So yeah, what we do is we'd find the critical points. You would notice here that the critical points are only plus or minus 2. So because the numerator is never 0, right? It's x squared plus 4 that never hits 0. So the only things to test are plus or minus 2. And so now I'm just going to plug in random numbers in between here. So like a -3, a 0, and a 3. And I'm going to plug into the first derivative. And one thing you can notice is that denominator is always positive because it's a square. So whenever it's not 0, it's always positive because it's all squared. You'll also notice that x squared plus 4 is always positive, and then I take a negative of that. So one thing you notice, it's always negative. So that actually wasn't so bad. You didn't even have to plug in. Well, you could plug in the numbers and see this, but it's also relatively easy to see that that has to be negative all the time. X squared plus 4 is always positive. I take the negative of it, now it's always negative, and I divide it by a square. So it's going to always be negative. So we're decreasing everywhere. So where are my intervals of increase? N/A. There are none. It's never increasing. Where are my intervals of decrease? Well, it's going to be minus infinity to -2, -2 to 2, and 2 to infinity. So I mentioned in the instructions earlier that type INF for infinity. So yeah, so that's 5.3 and 5.4. Let's move on to 5.5. Where is it concave up? Where is it concave down? So these are also two of the two kinds of things. For this, for 5.5 and 5.6, I would do the concavity test. Which means I'm going to do the thing essentially exactly the same that I did before, except with the second derivative. And it's just now positives and negatives will have a different interpretation. So whenever I see positive, I would now interpret that as concave up. Where I see negative, I would interpret that as concave down, as opposed to interpreting it as something like increasing or decreasing. But it's essentially just doing the first derivative test, but you're doing it with the second derivative. So now I would find the critical points. And with a lot of practice, you'll be able to do this just by looking at it. I mean, hopefully you can see right away that x equals 0 and x equals plus or minus 2 are the critical points here. I'm going to test this in the second derivative. Going to plug in a bunch of numbers like a -3 and a -1 and a 1 and a 3. I'm going to use the same sort of trick here of anything that can make my life a little bit easier. Notice that this part here is always positive. So I really only have to focus on the other part. So I'm going to focus on this and this. Just to save myself a little bit of calculations. So what I'm going to do is plug in a -3 into the 2x. I would get a negative. divided by, plug in a -3 into x squared minus 4, I would get 9 minus 4. That is a positive. So it's negative here, which means concave down. If I plug in a -1, I would get a negative. Plug in a -1 in the bottom, I would get a negative. So this here is positive, concave up. If I plug in a 1, I would get a positive. If I plug in a 1 in the bottom, I would get a negative. So this here is negative, concave down. Plug in a 3 in the top, I would get a positive. Plug in a 3 in the bottom, I would also get a positive. So this overall is positive, concave up. So now I can go back to the top and fill these guys in. So concave up, it's between -2 and 0, and then 2 to infinity. Concave down, it's between -infinity and -2, and then between 0 and 2. What are the x values of the x-intercepts? So this is taking it back. Usually we do this in step 1. So I go to the original function. I want my x-intercepts here. Right, set y equals 0, solve for x, you'll get x equals 0. If you set x equals 0, solve for y, you'll get y equals 0 as well. So I mean, it's the origin. So what are the x values of the x-intercepts? There's only one. What are the x values of any local maximum points? So going here is where I would check for maximum, but that's not going to have a maximum. In fact, it's also not going to have a minimum. What are the x values of any inflection points? Let's see, do we have any inflection points? So notice here, this is where, and this would reinforce what we did in part 1, where it's important that just the signs of the derivative is not enough information. Notice that here, f not continuous. It's not in the domain. It's also not continuous here. So those can't be anything. They're not points. However, this one, f is continuous there, is an inflection. And I know the x value for that. And that was that. FYI, do I remember? I think the graph looked like that. Well, just me looking at what we have so far makes me think it's like that. But I'll double check that. I didn't ask you to sketch it here, but on a test you would have to sketch it. So I figured I'd just draw a rough sketch for you guys. So yeah, problem 5. That was a long one, but that's actually pretty normal, as I mentioned. So if you're very annoyed by problem 5, don't be mad at me. It actually means I was doing my job well. Yeah, because it turns out just being able to test your idea of these concepts is a very nuancy kind of thing. Curve sketching is the only thing where I can concretely kind of know, okay, this person knows what concavity means. They know what increasing means, but it happens to be an annoying way to test it. But if you're going to test something that's very nuanced in a concrete way, chances are that's going to be annoying. So yeah. So sorry, not sorry. Okay, all right. Consider this function on that interval. Find the absolute extrema. So this is the name of the thing just slipped me. The closed interval method. It's too early. It's too early. I've barely taken any sip of my coffee, so geez. The closed interval method is the name of the method. It's hard to remember because it actually, nothing in the name actually says what you're doing. They should have called it like the absolute extrema method or something like that, and I'd remember it. All right. So it's one thing, math people name things by very boring, straightforward names usually, and it's like when you've had a long day, you start to appreciate it. So you're like, oh, math people are creative. Like, no, there's a reason. When we have all these theorems in our head and you want to reach for something, you want it to just look like the thing you happen to be working on at the moment. So you just call the name of the thing you're working on. It makes sense. Okay, so consider this function. So we're going to want to do the closed interval method. So remember, we're going to find the critical points and test them. So this means I'm going to find my derivative, which is 2/3 x to the minus 1/3. Critical points. F prime equals 0 or undefined. It turns out it's actually never 0 here, but it is undefined when x equals 0. Because this guy is actually 2/3 times the cube root of x. So if my x is 0 in the denominator, that's a problem. So x equals 0. And so what I would do is I would now evaluate at f at 0. The original function, x to the 2/3 is okay at 0. It's actually 0. 2, you're going to test the endpoints. So we were told x equals minus 1 to 27. So I'm going to find f of minus 1. I'm also going to find f of 27. This is minus 1 to the 2/3. Well, that's of course minus 1. And this is 27 to the 2/3. I would take the 1/3 power first, the cube root first. That would give me 3. And then take the square, which is 9. And 3 now you compare. Who's the biggest and who's the smallest? Of course, f of 27 equals 9 is going to be your absolute max. Who's the smallest? The minus 1. F of minus 1 equals minus 1 is your absolute min. And then I select that here. So first of all, this part here, hopefully you realize that that's impossible. Violates the extreme value theorem. So again, you have some ammunition for to go back and correct some mistake from problem 1 if you made it. And yeah, it's none of these, it looks like. This should have been a minus 1. And that would be right. Okay. Yeah. So there we go. That was the test. But we do have some time, a lot of time left over, even with all our dilly-dallying, for the bonus problems. So let's actually go through those because these were topics that they will be on the next test. and we have time to do them. So let's do them. So I don't know if you managed to watch ahead and get these done, but let me just run through these for you. And then if you watch the lectures after the fact, you can come back here and you can check that these answers actually match up. So it's pretty much standard procedure and standard knowledge that if this guy you compare to the generic integral from a to b of f of x, if you didn't read ahead, you won't even know what the symbol means or what the word integral means or something like that. And that's fine. I guess afterwards you can go watch it. Don't leave though. Remember, we still have an activity to do at the end. So stick around until the end. It's very important. So everything is set up based on that formula, and it's known. Well, it would be known if you watch the lectures, that delta x is always b minus a over n, where n is the number of subintervals or the number of rectangles used. So here your b is 2, your a is 0, and your n is 4 because of here. So that becomes a half. What is the left-hand approximation of the integral with 4 subintervals? So again, you knew what this was. So we are going from 0 to 2 with 4 subintervals. So that's 1. So obviously this point here is going to be a half, and this point here is going to be 1.5. And it says the left-hand approximation rule. So you pick all the guys that are on the left of each subinterval. And so your left with 4 is actually going to be, so this integral, 0 to 2 of our function, x squared, is going to be approximated by L4, which is going to be just delta x times f evaluated at all these points. So delta x we know was a half. F of 0, because our f of x is the x squared. 0 squared is 0. A half squared is a quarter. 1 squared is 1. 3 over 2 squared is 9 over 4. So that's 9 over 4 plus 1 over 4 plus 4 over 4. So that's 14 over 4. And so that's 7 over 4. What is the exact value of the integral? So we're going to learn, if you watch the lectures, you're going to learn about things called antiderivatives and certain formulas and what they are and all that stuff. And then you're going to learn something called the fundamental theorem of calculus, something that I talked about way back in lecture 1. And it's actually going to tell you a shortcut to finding this integral exactly, which is interpreted as the area under the curve. So it turns out that to find this guy, you would find the antiderivative of x squared, an antiderivative, which is going to be x cubed over 3. You're going to write this little symbol here. And again, you're going to plug in the 2. Minus when you plug in the 0. And the exact answer is actually 8 over 3, which is none of the above. And how that's interpreted is if you had the graph of f of x equals x squared, and you look between 0 and 2, and someone were to ask you, what is the area under that curve? The area is 8/3 squared units. And believe it or not, the ability to find the area under a curve is super useful. It's not even funny. Unfortunately, in this class, it's Calc 1. You're not going to see a lot of uses for it at this point. Calc 2 is normally where you do applications of integration and what you can do by being able to find the area under the curve. A lot of students in this class, though, do not need to do Calculus 2. So some of you will probably be in the dark on this for a long time, and you're like, oh, Calc 1, I never used that in my life. You know, I could be finding the area under the curve. It's actually really, really useful. I mean, just think about it. Most of this class, we were applying things to doing application of derivative, optimization, related rates. We could do a lot of things with derivatives, find when things are increasing, decreasing, find where something hits a max or a min, just by being able to find slope, right? It turns out being able to find areas is in some scenarios way more useful, and it's very applicable. But Calc 1 is not usually the course that goes into that. The function f of t represents the acceleration of an object. What is the interpretation of its antiderivative? So antiderivative means going backwards one derivative. And so we know that acceleration is the derivative of velocity, or you would know if you watch the lectures. Acceleration is the derivative of velocity. Therefore, the antiderivative of acceleration is velocity. I know the next one was very tempting. You probably, especially after question 5, you thought, Jhevon is a real jerk. You'd probably put jerk as the answer. Jerk is actually a real thing in physics. It's the derivative of acceleration, but it is not the answer here. And here's something with a picture. I'm not sure why I put that blank there, that blank space there. Am I missing something? Hopefully not. Below is the graph of a function, f of x, okay? So this is y equals f of x. Okay, got it. Compute the integral of this. And I mentioned here, notice that the thing in the integral is f prime, not f of x. However, we knew that the fundamental theorem of calculus, which is affectionately abbreviated FTC, we know that the integral of f of x dx is equal to big F of b minus big F of a, if your f is continuous on the interval and blah, 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 all that stuff, right? I'm just writing down the equation from the fundamental theorem of calculus. So the equation in, right? Because there's all sorts of these conditions that have to be fulfilled in order for this to be true. And of course, it's where the big F is the antiderivative of the little f. And of course, I don't want to say the, antiderivatives aren't unique, an antiderivative. Of course, an antiderivative of f prime of x is f of x. Now, normally there's going to be a constant here or something else. And so, but for this problem, you don't actually have to worry about that. So in other words, i.e., essentially what I'm saying is the following. If you look at the integral from -1 to 2 of f prime of x dx, this is just going to be the antiderivative, which is the original f evaluated at 2, minus the antiderivative, which is the original f evaluated at -1. And so you just want to find what is f of 2 and what is f of -1, which you can do that from the graph. F of 2, boop, boop, f of 2 equals 2. And f of -1, boop, equals 0. So it's somewhat of a conceptual question. If you understand the concept and you look at the graph, you'll see the answer. Yeah. So we're done with the test. Hopefully that was okay for everybody. And I assume if you have any questions, I would say test out the Piazza thing that I mentioned just to get your feet wet. It can be an incredible resource moving into the final. So I would highly recommend you trying to get onto that. Now, officially, I'm going to end the class here. I'm going to stop the recording, but don't leave. We are going to do an exercise where I want to put you guys into groups. So just stick around for a little bit more. We still have a couple people missing, but I think we have enough to actually make this useful. So that being said, let me say goodbye to the camera. So we're going to say goodbye to our online audience, but we're going to stick around. So hopefully that was all great. If you have any questions, answer me, blah, 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 usual boilerplate. I will see you guys in the next one. Ciao. All right.